Okay, so we proved Newton's theorem. I now want to show you an example, okay? And let's consider a simple example, something that's familiar. So we will work in mechanics, okay? And the symmetry I want to talk about is time translation invariance. So time translation invariance. Now, what do we mean when we say that time translation invariance is a symmetry of the laws of physics? Well, it means that the laws of physics don't depend on time. If I showed you a video of something happening, a ball bouncing against a wall or something like that, and I asked you, when was this video recorded? Well, you cannot tell because, the way the ball bounces around is the same no matter when you throw the ball. And that's because the laws of physics are not changing. They're staying exactly the same. So this is the symmetry that we're talking about. And as a consequence of this symmetry, we're going to learn that energy is conserved. So energy is conserved because the laws of physics yesterday were the same as they are today, and tomorrow they'll still be the same. So we're going to consider a particle moving in a potential. So we know what the Lagrangian is. It's 1/2 m dx dt squared minus v of x. That's the Lagrangian. And we also know what the equation of motion is, okay? So the equation of motion is mx dot dot is equal to minus dv dx. And then, as I said, I claim that the conserved quantity is the total energy, and you know that is nothing but the Hamiltonian. So let's just check that this is indeed conserved. So let's calculate what is dH dt. So this is equal to, so if we differentiate the first term, well, we have to differentiate x dot squared. So we'll get a 2. Let's just leave an m. We leave one of the x dots alone, and when we differentiate the second one, we'll get x dot dot, okay? So that's the answer from differentiating the first term with respect to time. Then when we come to differentiate the potential with respect to time, well, the potential only depends on time because it depends on x. So using the product rule, this is dv dx, and then we differentiate x with respect to time. Well, let's take an x dot out, and we're left with mx dot dot plus dv dx times x dot. But we know that mx dot dot is minus dv dx, so mx dot dot plus dv dx is equal to 0. So indeed, the energy is conserved. Now let's try to get this by applying Newton's theorem. So to apply Newton's theorem, we know that the Newton charge is equal to dl dx dot times by delta x minus f. And let's calculate the different ingredients that are going into this expression. So this is equal to. So this is the Lagrangian over here. So this is, of course, just m over 2 x dot squared minus v of x. So if we work out what is the L dx dot, well, we don't hit the v of x term because remember we treat x and x dot as independent variables. But when we hit the m over 2x dot squared term, we'll end up getting just an mx dot. So that's great. We know what the L dx dot is. So the L dx dot is just mx dot. Now let's work out what delta x is. So now we want to get hold of delta x. Now remember what we do? We change t into t plus epsilon. Epsilon's infinitesimal. So that means that x of t goes into x primed of t, which is equal to x of t plus epsilon. And then expanding this to first order in epsilon, we work to first order because epsilon is infinitesimal. We just get epsilon dx dt. So x primed of t, which is equal to x of t plus epsilon x dot, and this is x plus delta x. So comparing, there is delta x, there is epsilon x dot. So delta x is just epsilon x dot. And now we need to get hold of f. Now remember what we said? The change in the action should be equal to an integral dt, so total derivative of df dt. So let's calculate what the change in s is, and we'll be able to see then if it is a total derivative or not. So first of all, we know that x prime is equal to x plus epsilon x dot. So if we differentiate this another time, we will learn x prime dot is equal to x dot plus epsilon x dot dot. So the change in x is epsilon x dot, and the change in x dot is just epsilon x dot dot, okay? So that we're going to want to use. So the change in the action will be an integral dt, the change in the Lagrangian. And remember, the Lagrangian depends on x and x dot. So just using normal calculus, this is an integral dt. And what is the change in the Lagrangian? Well, it will be dl dx times by the change in x plus dl dx dot times by the change in x dot. And we know what the Lagrangian is. Okay, we wrote it down already. It's just m over 2x dot squared minus v of x. So if we calculate what is dl dx, this will be an integral dt, we'll have minus dv dx, and then delta x is just epsilon. So let me pull the epsilon up front. That's going to multiply everything. X dot plus, and then dl dx dot, this we already calculated, is just mx dot. So we'll have mx dot, and then we need to multiply by delta x dot. Now delta x dot is an epsilon, I pulled it out, times by x dot dot. Okay, so there we go, x dot dot. And now I want you to notice two things. So first of all, dv dx x dot is nothing but dv dt, because the potential only depends on t through its dependence on x, okay? And then secondly, mx dot x dot dot is equal to d by dt of m over 2 x dot squared, okay? So that's a relatively straightforward formula to verify. But using that, you see, we can now write the change in the action. So this is the quantity that we're studying over here, is equal to an integral dt d by dt. And now for the first term, we're going to write minus epsilon v. And for the second term, we're going to write plus epsilon m over 2 x dot squared. And this is indeed equal to a total derivative. So in fact, if we want to read off what f is the thing being differentiated. That's what f is, okay? So let's put in f. So f here, this is minus, we had m over 2 x dot squared minus v, okay? Let me just show you. M over 2 x dot squared minus v. Oh, and one thing that I did not put in that I should have is that both of these terms are multiplied by epsilons. Very good. And we now have evaluated Q completely. So let me clear a little bit of space and we'll just work out what we get. Okay. And that's certainly enough space. Let's go back to pen and black. So this will be equal to the first term is epsilon mx dot squared minus the next term is epsilon m over 2 x dot squared, and then a minus times a minus is a plus epsilon v, and epsilon mx dot squared minus epsilon m over 2x dot squared is just epsilon m over 2x dot squared. And then we've got plus epsilon v. So let's put the plus v here. We'll take the epsilon out. And this is nothing but epsilon times the Hamiltonian. And that's exactly what we wanted to demonstrate. So you've seen that we've obtained the Hamiltonian as the conserved charge associated to time translation invariance.